In this video, we're going to discuss weak acids and bases. What does it mean to be a weak acid and base? That you do not fully dissociate. Where a strong acid broke completely apart into H plus and counterion, a weak acid only partially falls apart. Some of the acid molecule is still intact. So molecules such as acetic acid will break apart into H plus and AC minus, but before all the acetic acid can break apart, well, acetate and H plus actually can react with each other to go backwards. Not all of the acid will successfully fall apart, and instead you'll end up in an equilibrium reaction. As a result of this, you end up having acid molecules, hydronium ions, and conjugate base. If you can do the reverse reaction, AC minus has to act as a base to pick up that H plus to go backwards. Weak acids always come with a matching base that just has one less proton. If we have ammonium, this is in equilibrium with H plus and ammonia. Ammonium can give away one H plus, and so is the acid. Ammonia, NH3, can pick up an H plus and is the base. All of our weak acids come with a conjugate base that goes with it, which is basically just the remaining part of the molecule when the H plus comes off. So I have a ammonium. The hydrogen leaves, leaving behind its electrons. So you end up with an electron pair there, and you get H plus and ammonia. When the acid did its job of giving away H plus, the remaining component just became the base, because that ammonia can loan its electrons back to the hydrogen to reform that bond. As a result, we can't calculate these stoichiometrically. You can put 1 mole of acetic acid into 1 liter and have 1 molar acetic acid, but that does not give you 1 mole of H plus. Determining how much H plus you have requires us to use the equilibrium expression. Remember that the K of equilibrium is equal to the product over the reactant. Well, our products, when we write our acid breaking apart, is H plus and base over our acid. When we arrange an equation like this, with the acid being the reactant and the H plus and the base being the product, we call that equilibrium constant the Ka, the equilibrium constant of the weak acid. Every weak acid has its own Ka. For acetic acid, for vinegar, it's 1.8 times 10 to the minus 5. For ammonium, the Ka is 5.6 times 10 to the minus 10. Those acids will reach equilibrium based on how easily they can give away H plus and how well their base can pick up H plus. This requires a little more math than stoichiometric calculations, however. So let's look at 1 molar acetic acid, and we will find the pH. If we were 1 molar HCl, that'd give us 1 mole of H plus per liter. That would be pH of 0. Well, in this case, I have 1 molar acetic acid. How much H plus is that actually going to give us? For this, we have to think about the equilibrium process. I've got acetic acid in equilibrium with the H plus and the AC minus. At the very beginning, in the initial steps, let's assume we have 1 liter of this, so our moles are equal to our molarity. So at the very beginning, I have 1 mole, let's say 1.0 mole of acetic acid. And I'll have none of the products yet. We're assuming that our acid is better at being an acid than water, so it's going to overpower whatever water would have. So we're not concerned about the naturally occurring H plus from water. As long as our concentrations are reasonably large, they will dominate over the naturally occurring H plus. So we can assume that there's none of these products yet. But slowly, some of our HACs are going to break apart. We'll start with a bunch of acetic acids. And over a little bit of time, eventually some of them will separate. Over a little bit more time, more will separate. And over a little time, maybe another will, but one of them will pair back up. And eventually we'll reach equilibrium for breaking apart and repairing. But the idea is I can't get any products unless some of my starting material breaks apart. So there's going to be a change. I'm going to lose some of my starting materials. Well, every time one of them falls apart, I'm going to make just as many of my product. For every one acetic acid that breaks apart, I'll get one acetate and one H plus. So I don't know how many that is, but whatever the amount is, it has to be the same across the board. Eventually, I will reach equilibrium, though. What will that concentration be? How much acid do I have left? How much of the products have I made? Well, that's going to be the original amounts with the adjustments. So at equilibrium, I'm going to have my original amount of acetic acid minus whatever broke apart. So 1 mole minus X moles. My H plus is just going to be equal to however much got formed because it started at 0. And my AC minus is going to be equal to however much formed because it started at 0. Well, these are all in 1 liter, so our moles are equal to our molarity. I can plug this back in to our Ka expression. My Ka has to equal my H plus times my base, which is AC minus, all over my acid. Well, I have those amounts in the volume, so I can say, well, my H plus is going to be equal to X molarity, X moles per liter. My base is also going to be X moles per liter. And my acid, well, that's going to be 1 minus X. All that has to equal our Ka, which, said above, for acetic acid is 1.8 times 10 to the minus 5. Well, it's possible to calculate this out with the full quadratic. You can multiply the bottom up, you'll get x squared, you can rearrange, and you'll end up with 0 equals x squared plus 1.8 times 10 to the minus 5x minus 1.8 times 10 to the minus 5. As you rearrange this, you can actually set it up to do the quadratic. Hey, negative b plus or minus the square root of b squared minus 4ac divided by 2a. I know maybe in 8th grade you didn't believe your math teacher that you'd ever actually have to use the quadratic, but here it is again. It shows up with equilibrium calculations. Today we don't have to though, because luckily for most weak acid-base systems, we can simplify this quite a bit. If we think about this for a minute, I'm going to subtract x. My expression says it's my products over my acid, and it has to be, well, kind of small, 10 to the minus 5. When you think about division, if you want something that small, then your top number needs to be very tiny. Our top needs to be really small so that when I do the division, I get a small number out. X can't be that large. Otherwise, we'd end up with a lot on top and very little on bottom. But based on my Ka, I know I need very little on top and a lot on bottom. So logically, we can't subtract very much from 1, and we can't put very much on the top. As a result, well, if you have 1.0 and you subtract, say, 0.0002, so a small amount by comparison, 0.9998. Well, if you only had 2 sig figs, that's just really going to round back to 1.0. We are definitely losing some starting material, but within our sig figs, it's really going to look like it's the same amount. Whatever we actually subtract is barely going to change the concentration we started with. As a result, this can simplify our calculation. We can kind of ignore that minus x. This makes our work much simpler because then we just get x squared is equal to 1.8 times 10 to the minus 5. Our 1 on bottom multiplied above, well, 1.8 times 10 minus 5 times 1 instead of 1 minus x just gives us 1.8 times 10 to the minus 5. Take the square root of both sides, and we can solve x. No quadratic necessary. This is convenient and often the case with weak acid calculations. So we started with our initial concentrations. We identified that there's going to be some change. We found what the equilibrium concentration should be. We can simplify out the minus x, because as long as our concentrations are reasonably large, x is going to be really tiny by comparison. So within rounding error, we can just keep the original amount. Anything greater than 0, though, is relevant. We can't get rid of x for our products. And so calculate amount 1.8 times 10 to the minus 5 square root 0.00424. And yeah, that's pretty small compared to 1. So not too far off to forget to subtract the x. But that is our concentration of H+. We said H+ was equal to x. And so I have my concentration of H+, which means we can find the pH. pH of the negative log of 0.00424 gives us 2.37. Well, a strong acid in a 1 molar solution would give us a pH of 0. Our weak acid, acetic acid here, gave us a pH of 2.37 because not all of the starting material had fallen apart. In fact, compared to 1, 0.4% had fallen apart. 99.6% of the vinegar molecules are still intact. Only 0.4% actually fell apart, but that's still far more H pluses than would be from neutral water. And so we have a reasonably acidic solution. When it comes to weak acids and bases, we must use our equilibrium calculation to solve our H plus concentration to find our pH. We cannot simply use stoichiometry to find out how much H plus there is.